The next part of question 5 is about halogen displacement reactions. This is a hugely important type of reaction. You've got to make really sure you've understood these and can go through all the stuff about what you would observe, how you'd write the equations, how you'd explain it in terms of oxidation states, and so on. It's very, very likely to come up in the exam. So, before we actually answer the question that's on the paper, let's just remind you about that chemistry. So what it's asking about here is what happens when you add bromine in the form of the element to either chloride ions or iodide ions. So what you're setting up in each of these experiments is a straight fight between two halogens. In this case, the chloride ion has already got an extra electron, the bromine hasn't, but it would like one, and so they fight over the extra electron, and the question is which one wins. So what you've got to remember is the answer is that the element higher in the group always wins, always ends up as the negative ion. And we'll explain that in a moment, but make absolutely sure you've learnt the trend, that the elements become less reactive, is what people usually say as you go down the group. Okay, less reactive meaning less good at attracting an electron into the outer shell, and therefore the element higher in the group will always end up as the negative ion in these reactions. So in this case, bromine will fail in its attempt to grab the extra electron from chloride because chlorine's higher in the group. So the answer is no reaction in that case. But now when bromine tussles with iodide, this time the bromine will win because bromine is higher than iodine in the group, it's more reactive, so it will succeed in grabbing the electron away from the I- ion. So here you will get a reaction, meaning the bromine will turn into Br- and the iodine will turn into I2. Okay, so that's the basic idea. Make sure you've got all that sorted out, and then you can think about what you would actually write. Because you've not got that much space available. You can't afford to waffle on with all kinds of random, not very relevant things. It gives you the bullet points to tell you what you've got to cover, and you've got to make sure your answer focuses on that. Okay, so keep all those ideas in mind, and now we'll see what we've actually got to write down. So first of all, let's talk about the trend. I know it's the third bullet point, but you don't have to do them in the order they're listed. Do them in the order that makes most sense to you. So the trend in reactivity is that reactivity decreases down the group. Okay, down group 7. And that means, remember, that they get less good at attracting an electron to form a negative ion. Why is that? Because, for the same reason that ionization energies decrease as you go down the group, because you're adding extra shells, so the outer shell is at a greater distance and is more shielded, so there's weaker attraction to the nucleus. So use that same checklist that you used for ionization energies. So you can say because the outer shell becomes more shielded further from the nucleus, you could say this outweighs the higher nuclear charge, as you would do in an ionization energy question, although that wasn't really required here. But you should certainly bring those ideas together. So, weaker attraction to the nucleus. Okay, so that's the trend in reactivity, and that's the explanation. Then we've got to come to the specific experiments, and it says, what colour would you see in the cyclohexane? So cyclohexane, remember, is just a solvent. It doesn't take part in the reaction, but what it does is, whatever halogen, whatever element is there at the end of the reaction, it extracts it from the solution and lets you see the colour of the element very clearly. So in the first case, where we had bromine plus chloride ions, we decided there would be no reaction. So there's no equation to write, but we've got to talk about the colour. And the colour we'll see is the colour of bromine, because no reactions occurred, so it hasn't turned into anything else. Chloride is colourless. Remember, the negative ions don't have any colour, so it's the elements that we worry about, and we get an orange solution in cyclohexane due to Br2. Okay, so that's very straightforward. That's actually all we have to say about that reaction. Because there was no reaction involved, there's no equation to write. But when we have Br2 plus I minus this time, we did have a reaction. So it asked for the ionic equation. And that means you need Br2 aqueous plus 2I minus. Okay, 2I minus, because each of those bromine atoms is going to become Br minus. So they each need to grab an electron from an I minus. So that will give us 2 Br minus plus I2. And that's your equation. The colour this time will be the colour of iodine. Okay, because the bromine has gone, it's been used up in this reaction, and what we generate is iodine. And again, you have to learn that iodine dissolved in cyclohexane is purple. Okay, so you get a purple solution due to I2. It's worth knowing that iodine is brown when it's dissolved in water, but it becomes purple in the organic solvent. And that's really why you do that, because it makes its colour very easily distinguishable from bromine, whereas in water they can be sometimes quite difficult to distinguish if the solution is a bit dilute. And that is actually all that you need to say, because if you just check your bullet points, we've covered everything, and that should be all of your marks. Why did the student carry out the reaction in a well-ventilated area? Simply because bromine is toxic. In questions like that, those safety questions, you just have to avoid using excessively vague words like dangerous or harmful. They don't like those words because, you know, harmful could mean toxic, but it could also mean, you know, explosive or radioactive or likely to leap up and punch you on the nose. You've got to specify in what way it endangers you. So toxic is the sort of word to use. On to the final page, and we've got to look at this reaction of fluorine and water. So fluorine is also in group 7. You don't have to learn anything about fluorine other than that it's at the top of the group, so it, you know, will be the most reactive element. But they quite often ask you about it, and you just sort of have to use the things you do know about and sort of extrapolate them to fluorine. So we've got F2 plus water turns into something plus O2. Well, if you look at the elements, you can see that once the oxygen comes out as O2, what you're left with is hydrogen and fluorine. So this product is going to be HF. And because you're doing it in water, just like HCl is very soluble in water, so too is HF. So that's going to be aqueous, and the oxygen obviously is a gas. That equation now needs balancing. Remember, never ever leave an equation unbalanced. So we've got 2 fluorines, 2 hydrogens, so 2 HF, only 1 oxygen, so we can only have a half an O2. If you don't like the half, you can have 2 F2s, 2 H2Os, give you 4 HF and an O2, and that would be fine as well. But there's no problem with half, so that would be the easiest way to do it. Only 1 mark for that, which was a bit mean. Now we've got to do the oxidation number thing. Remember, oxidation number, oxidation state, doesn't matter what you call them, it's the same thing. So we go through and apply the rules that hopefully you've been learning. So fluorine is an element, and elements, remember, have an oxidation state of 0. In water, you use the rules about hydrogen and oxygen. But in compounds, oxygen is nearly always -2, and for AS purposes you can safely assume it's always -2 in a compound, not if it's elemental O2 of course, but otherwise oxidation state is -2. And hydrogen in compounds, again you can assume for AS is always +1, so 2 lots of +1 is the oxidation state there. In HF, Again, the hydrogen is +1, and the fluorine, therefore, is going to have to be -1, because remember that in compounds, if it's a neutral compound, the sum of the oxidation states has to be 0. So if this is +1, that has to be -1 to balance it up. And oxygen is an element, so that's back at 0 again. Okay, so they're quite easy to assign, and then you just have to decide what's oxidized and what's reduced. So you look at what changed, and you see the fluorine goes from 0 to -1, which is less positive, is what it's becoming. And if something's less positive, that means reduction. So the answer is the fluorine is reduced. And what gets oxidized? Well, the hydrogen stays the same, because it's +1 here and it's +1 there, but the oxygen goes from -2 here to 0 there. So the oxygen becomes more positive. -2 to 0 is more positive, which means the oxygen is oxidized. Which is an odd statement, but you can see it's because fluorine's a bit special, that it can actually oxidize oxygen. And specifically, what you should say, because it's always slightly unclear, what should you say has been oxidized, the oxygen or the water? So the best thing to say is that the oxygen in H2O has been oxidized. And then you've covered all the bases and you're definitely going to get the marks. Okay, so the F2 is reduced, but the oxygen in H2O has been oxidized. And finally, electron structure of a gallium atom. Okay, so we're into the 4th period here. So use your periodic table to guide you as you go through to get these electron configurations right. So let's just clear a bit of space for this one. You go across the first row, just 2 elements gives us 1s2. Second row, 2s2, 2p6. Third row, 3s2, 3p6. And then when you get to the 4th row, we have the complication that you've got the first transition series in, which remember comes from filling up 3D. So by the time we reach gallium, we're already past that, so we filled up the whole of 3D, 3D10. We've also filled up 4s, because that was back in the S block, with potassium and calcium was where we were filling those. So we've got 3D10, 4s2, and then we're into the P block again. We're starting to fill up 4p, and gallium is the first element in the P block, so it's 4p1. If you wrote 3D10 and 4s2 the other way round, because the order they're filled up is 4s2 then 3D10, that's fine. They're not going to worry about that, so long as you've got them both in there. And the empirical formula of gallium fluoride, well, the point is that it's in the same group as aluminium, so you're going to expect it to do the same kind of thing as aluminium, which means that because aluminium fluoride is AlF3, because you have Al3 plus balanced by 3 F minus ions, that you would expect gallium fluoride to be GaF3, presumably having Ga3 plus and 3 F minus ions. And that is the end of the entire paper.